All right, guys. Happy Friday. Woo. What better way to start a happy Friday, a happy weekend than with organic chemistry? All right. That's what I thought. All right. Let's pick up where we left off the other day. So we had started up in chapter 12. And so we were just starting to go over some oxidation reduction. And I think, let's see, what did we do? I think we got through reduction of alkenes to alkanes. We did that? Give me a yes or no, just to make sure, because, okay. I didn't have any notes that day, so I was just kind of going off the top of my head. All right, so let's continue with that discussion. Now, this actually kind of leads into a really interesting kind of real world type of application where we can see this done. This reaction is done a lot in food chemistry, right? A lot of the foods that you eat will have had this reaction actually performed on them, okay? I'm guessing you've probably heard from, advertising, maybe a nutrition class or something like that. You've heard of like saturated and unsaturated fats before. See some nodding. Heard of trans fats. Heard the terms monounsaturated, polyunsaturated, et cetera, et cetera. Yeah, so, and you know that some of them are supposed to be the good fats and some of them are the bad fats, right? What are the bad ones? Y'all remember? Saturated are supposed to be bad, all right? There's also another bad one. Trans fats, yeah. So saturated fats and trans fats, those are the bad ones. Unsaturated are the good ones, right? Specifically, polyunsaturated are the really good ones, right? So obviously you've heard all this before. Do you know why some are considered good and some are considered bad? At a molecular level. You've probably wondered that many times before, I'm sure. But now, guess what? It's your lucky day, you get to find out, all right? Now, so yeah, I'm gonna show you how this applies to the fats and everything. It gets a lot more complex than what I'm gonna go into. You'll learn more about that if and when you take biochemistry, right? But this is sort of a little preview to give you sort of a basic explanation. Here's what a fat looks like, fatty acid. And saturated fatty acid looks like this. First of all, we call it fatty acid because it's got a carboxylic acid group on it, right? And then it also has a really long hydrocarbon tail. I don't even know how many carbons I just drew. I just know I drew a bunch of them, right? And there's different types of fats with specific numbers of carbons. This is an example of a saturated fat. The term saturated comes from this hydrocarbon tail, right? And it refers to the fact that every single one of those carbons has the maximum number of hydrogens that it could possibly hold, right? So for example, if I just randomly chose this carbon right here, since this carbon is linked to two other carbons, what's the maximum number of H's it could hold theoretically? 2. And guess what? It does. It has 2. Every single one of these carbons has the maximum number allowable, so it's saturated with hydrogens. Right? So that's where the term saturated fat comes in. Right? If you take something like this, and let's toss an alkene group in there. Then you change things a little bit, right? This carbon is linked to two other carbons, so theoretically the maximum number of H's it could have would be 2, but guess what? It's only got 1, since one of the links is a carbon-carbon double bond, right? So this is an example of an unsaturated fat. And then we can get a little bit more specific, right? Specifically, this would be an example of a mono unsaturated fat. Any ideas why we call it mono? It's only one area of unsaturation right over there. So we say it's mono. There's another term, another descriptor we can put on this based off of the stereochemistry around that double bond. What is the stereochemistry around that double bond? Strands, right? This is strands. This bond is pointed one way, this bond is pointed the other. So this is actually an example of a trans fat. And these are the ones that we consider bad. Both of these, all right? Any ideas on why they're bad? What do they do? Like if you consume like copious amounts of the bad saturated and trans fats, health-wise, supposedly what will happen or what could possibly happen to you? Clog your arteries, right? Right. Form these plaques in your arteries. Right? So if you think about what's happening there whenever you're forming plaques, and again, the process is more complicated. It involves things called lipoproteins and blah, blah, blah. But in a nutshell, what's happening is whenever you form these plaques in your arteries, you have a bunch of fat molecules that are accumulating together in a very small space, right? So you create this species, sort of this mass that has a high density, right? The higher the density, the more solid-like it's going to be at a room temperature, and this is how you get the deposits, right? How do you get very, very high dense accumulations of these molecules? You know how? They stack together like dinner plates, right? You know, you're putting up some, or let me say cereal bowls or something like that. You're putting up bowls in the cabinet, a bunch of them. What do? You stack them in each other, right? So you can fit a lot of them in a narrow space. Well, that's what happens with these saturated fats, right? Another one could come along with another hydrocarbon tail with this little zigzag pattern, and they can fit together very, very snugly. And then another one could come, another one could come. And since they fit together so well, you can fit a lot of them in a very narrow space. It means you make a very dense species. Right? How are these interacting with each other? Remember your intermolecular interactions from chapter 3? What type of forces are holding these hydrocarbon tails together? Everybody's giving me like the blankest look possible. You didn't tell me we'd be talking chapter 3 stuff.
At least dipole-dipole.
You probably would have some dipole-dipole if you had some like interactions over here, but they're not going to be the major ones of the tails. There's 2 left. Are those tails polar or non-polar?
Polar.
What's your second guess? They're non-polar. Non-polar, all right? You have 3 interactions, dipole-dipole. Those are involved in polar interactions. Hydrogen bonding and van der Waals. Which one of those is associated with non-polar species? The last one, yes. Van der Waals, right? So basically, you get these so close together, these van der Waals forces can add up. And even though they're the weakest ones, if you have a lot of them, they can accumulate pretty well, right? As you increase the magnitude of intermolecular forces, what happens to the melting point of something? Again, more chapter 3 stuff. It increases, yeah. So basically what's happening here is when you make these high density species, the magnitude of intermolecular forces increases so much that at normal room temperature, or in your case, your body temperature, these fats are in solid form instead of liquid form. If they remain in solid form, they can form blockages. Does that make sense? Let me elaborate on this and show you how other fats are the good fats. That'll probably help paint the picture a little bit. Right? Look at that. What's the major difference besides number of carbons? I'm trying to put the same number of carbons. What's the major difference between that one and the one in the middle of the board? Cis. This is a cis fat. Specifically a cis monounsaturated fat. All right? Now, whenever I put a cis bond in there, what did that kind of do to the tail? If you just had to sort of give a general description, how does it look different? Is it as straight and true as the trans? No, it's got a kink in it, right? It's gone kind of crooked. What do you think this has? What kind of implications do you think that has for stacking? What's that? Does not stack as well. Yeah. So when you start introducing cis double bonds in here, they don't stack as well. That means they can't get into these high density masses. Their intermolecular forces can accumulate, and they're going to have lower melting points. That's why polyunsaturated fats are considered better, because if you have polyunsaturated fats, guess what? You might have more than one cis double bond, and that's good, right? Does that make sense? Y'all ever, I mean, I'm sure you guys have seen, different margarines and stuff like in the grocery store. What do you guys prefer, first of all, butter or margarine? Really, people are usually really passionate about this. And I'm serious, like, maybe it's an adult old person thing. Maybe, you guys don't give a shit now, but when you get old, then you're gonna care. All right. Anyway, there's a little bit of a trade-off there as far as health. Margarine tends to have higher levels of trans fats. Butter tends to have higher levels of saturated fats, as well as cholesterol, but that's a whole other thing. Anyway, let's look at the margarines. You know how sometimes you get margarine, it's like in a stick, a hard stick, just like butter, or maybe in a tub, and it's really, you have to dig it out. It's hard to spread on your toast or whatever. Then you get other ones that are maybe kind of the squeeze kind, where it sort of comes out as like a little goo. And then you also have the spray kind. You ever use the spray kind? Yeah? Molecularly speaking, what do you think the difference between amongst those three is? Same identical temperature, but different forms. Pure liquid, pure solid, basically, and kind of a goo. What's changing there? Melting point. Yeah, and what's changing the melting point? The type of fats that you have. Yeah. So people, there's a lot of debate on, what constitutes what's healthier as far as butter or margarine. A lot of it's based off of, what's artificial or natural. That's a whole other soapbox I could get on top of. But basically, in a nutshell, for heart health, the more liquid it is at room temperature, the better it is for you. Yeah, that spray butter, very high in polyunsaturated species, very less likely to clog your arteries. Those hard margarine sticks, those are going to have lots of trans fats, probably. Much more likely to clog. So basically what it's doing in the freezer section or the refrigerated section at the store, that's maybe how it would exist in your body. Does that make sense? So kind of a neat little application. Now, okay, I'm kind of getting off on a tangent here. How the heck does this relate to catalytic hydrogenation? Well, have you ever picked up some sort of ingredient. Maybe if you're anything like me, and you're probably not, you like to look at the ingredient lists on different things like even foods or shampoo or something like that. I'm a weird person, but I like to look at the stuff because, oh, look, I recognize that. I'm a chemist, I know what that is. But have you ever looked by any chance on a food product and seen the phrase partially hydrogenated oil before? If you haven't, take a look next time. Peanut butter has it a lot. Margarine. I think mayonnaise sometimes has it. I'm not sure. Shortening, like Crisco, that's probably going to have it in there. All right. Has anybody ever heard of it? I didn't see anybody nodding their heads. You have? Okay, cool. I'll pick on you then as a. Too late. Did you ever wonder what that meant?
Not one.
You didn't care at all, did you? Thank you. I mean, most people haven't. But now you can think of it. It's actually a very sort of weaselly marketing phrase. What you can do, you can isolate fatty acids from lots of things, including lots of plants. And that's obvious, right? You know, you have olive oil, you have canola oil. Those are all fatty oils that are isolated from plants, right? You see they're kind of viscous, but they're still kind of liquid at room temperature. All right, a lot of these oils, fatty oils that you can get from plants, are polyunsaturated. That means they're generally pretty good for you. However, when you partially hydrogenate something, that means you take this oil and you perform a catalytic hydrogenation on it. And as we learned the other day, if you perform catalytic hydrogenation on an alkene, what type of product do you make? An alkane. It becomes more saturated, right? So when you partially hydrogenate something, you're getting rid of these double bonds. You're making it more saturated. In other words, you're making it less healthy. So so for a lot of these products, the companies will partially hydrogenate and then put it in. That way, they don't have to say that they're including saturated fats. See, it's a workaround. Sneaky, sneaky. You may wonder, why the heck do they put those in there? Any ideas? Just from you don't even have to think from a chemist point of view here, just from a consumer point of view. Good thought. It's not actually cheaper necessarily. It'd be cheaper if they just put them in directly because anytime you perform a chemical reaction, it takes resources. So it's not money.
Maybe that it doesn't sustain your appetite.
Good point. Does it sustain your appetite? Does it satisfy your appetite better in hydrogenated form? I honestly don't know if that's true or not. So that's not what I was getting at, but it might have something to do with it. Generally speaking, that does help the shelf life a little bit. So that's part of it. Yeah, the fewer double bonds are more reactive than single bonds, right? So if you leave it on the shelf for a while, if it has more double bonds, it probably will, decompose a little bit. There's one other probably more important thing though, and you're probably not going to get it. Aesthetics. Think about it. Guys, a bunch of you were aware of the spray margarine. Do any of you actually use it? You do? Cool. Who prefer, let's see, I'll take a poll. Who would prefer margarine in a tub over spray margarine? Just for a health aside. Okay, who would prefer the spray? Like 2 or 3, okay. Why do you prefer the tub? Just curious for anybody who answered that you prefer the tub. What's that? What you're used to? Okay. Easier to visualize how much you're using? Okay. Yeah. Honestly, consumers just generally prefer to have something that's kind of spreadable. They can dig out, spread with a knife. The thought of like spraying their bread with this liquid is kind of icky. For peanut butter, Have you guys ever seen the natural peanut butter? What does it look like? All oily and kind of, you mix it up and it looks like big, gross, gloppy stuff. That one is healthier for you. That one has more unsaturated fats. You hydrogenate the oils, it becomes this nice, uniform, creamy texture, right? So a lot of it just has to do with, preferences of the consumer, spreadability, texture. That's why they hydrogenate oils. So, yeah, there you go. Pretty interesting little application. But yeah, they do this reaction. They do that reaction that I put up on the board the other day. They directly do that. They take these oils, they will bubble some hydrogen through them with a catalytic metal to make these oils. So if you have some peanut butter back in the dorm room, go back and take a look at it. And think to yourself, I learned something in organic chemistry today. All right. Okay, I'm about to move on to some other stuff. Any other questions or thoughts or comments on the fats? Okay. All right, so alkenes, it was pretty obvious we could hydrogenate because we had a pi bond. Hey, guess what? We have other things with pi bonds. We have alkynes, right? In fact, alkynes have more than one pi bond. So there's probably some more stuff that we can do with this. All right, so let's take a typical alkyne. All right, so we saw last time that you could take an alkene, go directly to an alkane, pretty easy. You can actually do that with alkynes as well. Through the same method, however, there's one extra thing you have to keep in mind. What do you think it is? We could do this, just with H2 and platinum, right? But there's one extra little notation we have to make note of here. What do you think it is? Yeah, you got 2 pi bonds that are being reduced, right? Not just one. So that means you need to do it twice. So make sure to have 2 equivalents. And the mechanism is exactly the same as we learned with alkenes. You just do it 2 times in a row. All right. So that's great. That's fine and dandy. What about if we want to stop at an alkene, though? What if we want to go directly from an alkyne to an alkene? And yes, I'm drawing it that way for a reason. You'll see in a second. Sorry, get the hiccups. All right, so you only want to do this once. How do you think we would do this here? Any logical guesses? What's that?
Don't put it so much in. Don't do it 2 times.
Only add 1 equivalent?
Yeah.
Excellent logical observation. That is incorrect. But it's the answer I wanted you to say because that's the one that makes sense, right? Actually, you couldn't do that. I'm going to show you why. Let's just assume that you did this. Let's say you added 1 equivalent of that, right? You do that, and yeah, you are going to make some of this, right? What did we just learn, though, the other day? If you have alkenes in the presence of H2 and platinum, are you necessarily going to stop here? No, you're not. Some of this is going to all convert all the way to the alkene. And since you only have 1 equivalent, since some of them get wasted over here, that means you're also going to have some of this left over. So that's a big old mess. So that's why we don't want to do that. So good thinking, but there is actually a problem. What would be great is if we could somehow temper the reactivity of this system, make it so that it reacts with an alkyne, but it's not reactive enough to react with an alkene. And lo and behold, there is a way to do that. What you do is you add one equivalent of H2, and then you add a very special type of catalyst. It's called a Lindlar catalyst. Right? And basically I'm not going to go into tremendous detail on what a Lindlar catalyst is. You can look in your book if you want to see specifically how it's made. Basically what it is, Lindlar is a palladium catalyst that's been poisoned. A couple of additives have been attached to the surface of the catalyst to make it a little less reactive. So it's strong enough to help react with an alkyne, but not strong enough to catalyze this reaction, that particular reaction with that particular product. So if you use Lindlar, you stop at the alkene. And that's nice. Gives you some options. Okay. All right. Now, I told you I drew it that way for a reason. How did I draw it? What am I representing? I didn't do regular zigzag. I did alternate zigzags. What did I draw here? Cis. I drew a cis representation. And that's important. Doing this reaction always gives you a cis alkene. Does not give you trans. Only gives you cis. Any ideas why? Why would that only give you cis? You guys know the answer to this. Even if you don't know that you know. Think about what actually happens in the mechanism. Look back in your notes if you have to. What happens in the mechanism of hydrogenation? What's that? We have a syn addition of the H's, right? Remember, you have the surface of the catalyst. The H's end up sort of planting themselves like little trees. And we showed this with an alkene the other day, but in this case, an alkyne could come fluttering by. Those H's are always going to add from the same side, right? So if we drew them out here so you could see them, that's where they are. As a result, the other two species are always going to be on opposite sides of those H's. Does that make sense? Does that make, excuse me, are there any questions on the reasoning there? Syn addition gives us only a cis element. Well, I know what you're wondering now. You're wondering, how fast can this next 20 minutes go? Alternately, you might be wondering, how the heck do I make a trans alkene? I'll show you that in a minute. Very soon. However, I want to highlight one more thing about catalytic hydrogenation. It's not just carbon-carbon pi bonds that you can target. You can target other ones as well. Specifically, you can do this to aldehydes and ketones as well. So you can target carbonyl groups. Carbonyl groups if they're in aldehydes or ketones, right? So basically, it works the same. Both of these atoms here will get H's. So with a ketone, you can get a secondary alcohol. Or if you use an aldehyde, You get a primary alcohol. And we'll come back to those. Those come pop back up in I think like chapter 17 or 18 or something. So we're not going to focus on these too much, but it is something that you should probably be aware of. You can do this with things other than carbon-carbon bonds. Here's a thinker for you. One equivalent of H2. Ooh, what do you think would happen there? This is a rhetorical question. You don't know. I'm not actually expecting you to know this. What's going to get hydrogenated here? Who says the alkene? Who says the carbonyl? Okay, now we're getting some votes. Okay. Who says a mixture? Ah, here's the preference. It will prefer the carbon-carbon pi bonds. So if it has a choice, it'll target carbon-carbon. However, if you just started off with an aldehyde, you could definitely get the carbonyl group without the competing carbon-carbon. All right. Any questions about any of the catalytic hydrogenations? All right, we're about to get into another method of getting H's onto a molecule. And we're going to go back to that question that I raised just a second ago. How can we make trans alkenes? We saw we can make cis alkenes. How can we make trans? Can we? The answer is absolutely. We can. All right, let's take an alkene. It's possible to make a trans alkene if you add 2 equivalents of sodium. And this is sodium metal. This is not ionic sodium, so it's not Na+. And 2 equivalents of ammonia, NH3. This is opposite to what you saw with the hydrogenation. This one only goes anti. So that's why it only makes trans. So it's kind of nice. You don't have a singular way of doing this that gives you a mixture of both. You can choose to do one or the other based off of what you want. Right? The mechanism for this one is going to be different, a little bit different than what you're used to. All right? It all starts off with the sodium. All right, so you got sodium. Right? Like I mentioned the other day, sodium's really reactive. It's really easy to oxidize. You stick it in water and it goes all over the place. That's because it's being oxidized. So that sodium very easily can give off an electron. I'm just going to represent the electron with an E. Just a singular electron. And this little electron can attach itself to one of the carbons in the triple bond. And in turn, that's going to knock one of these pi bond electron pairs for the other carbon. So you end up with a really weird looking species. It looks like that. Single unpaired electron on one carbon, unshared pair of electrons on another one. Y'all remember what the term is for a single unpaired electron? It is a radical. Yeah. So this one's a radical, and at the same time, it's an anion. So, hey, this is an example of a radical anion. I always say if somebody wanted to start their own punk band or something, then the name Radical Anions would be a fantastic name. So just keep that in mind. You know, if you're ever so inclined, give me a cut of the t-shirt royalties. All right, so you make the radical anion, right? That's where your ammonia comes in, your NH3. Basically, NH3 serves as a proton source, an H+, right? So this negative charge can grab a proton, and at that point, you're just left with a radical. Right? So you notice there's two equivalents of both of these species. We've used one of each. We're going to go through the cycle again. Let's see, we'll do it down here. The other equivalent of sodium gives off an electron. What do you think that singular electron is going to do? Just intuitively. What's that?
Go to the single one.
Go to the single one, yeah. Electrons, they like to exist in pairs, right? They don't like to be alone. They like to have a little electron soulmate. And so, yes, this is going to seek out the single electron over there. And that will make a pair of electrons. And now that we have an unshared pair, we have a full negative charge on that carbon. And lastly, that other NH3 can come in, donate a proton to that negative, and boom, that's how you get your transalkene. So it's kind of cool. You get a little peek into radical chemistry here. So definitely a different mechanism, but it works. And it's very reliable. You know, you do this with an alkyne, you're always going to get a transalkene. You do hydrogenation with Lindlar of an alkyne, you're always going to get a cis alkene. So you don't ever have to worry about mixtures of cis and trans. All right. For our purposes, this is pretty much the only thing that we're going to use sodium and NH3 for. There's other uses for it, generally speaking, but for our context right now, we're going to sort of leave it there. Okay? Are there any questions about that? All right, so we said there was a third way, one last way of getting hydrogens, extra hydrogens onto a molecule, right? And that's to use hydride, right? And don't forget I told you hydride is basically this. It's a negative hydrogen that's got a full unshared pair of electrons. To get hydride, guess what we need? We need a hydride source. One common hydride source is this. LiAlH4. That guy is called lithium aluminum hydride. Right? So you can do a couple of different things with this. All right, one thing that you can do is you can react it with alkyl halides. And actually, this really isn't a different type of reaction. This is the same type of reaction we've learned in the past, just with different species, right? For mechanism purposes, I'm going to rewrite this a little bit. I want to rewrite it like this. just so I can show you exactly what's happening with hydride. All right. What do you think? What do we use lithium aluminum hydride for? What do we want from it? What do we say? Not just the hydrogen, but the electrons that go with it. Yeah, we want hydride, right? We want H minus. That's going to be this. Think to yourself, what could hydride possibly want to do, given the presence of that alkyl chloride? Just kind of brainstorm. Exercise those critical thinking skills. You got an H minus. What do you think it might want to do? Which carbon? Attach the carbon with the chlorine. Why that one? Yeah. Don't ever forget the basics. Positives and negatives are attracted to each other, and this includes partial charges. This is just a straight up SN2 reaction from chapter 7. The difference is we haven't seen hydride as a nucleophile yet. So yeah, it's going to proceed just like one of those reactions. H minus can come in. It can knock off Cl minus, and you get a straight up substitution. Oops, I put an extra carbon in there. The water is required, but actually does not show up in the mechanism. And that's it, right? Just a straight up SN2 reaction. This is a reduction because as you go from reagent to product, you have fewer bonds to electronegative atoms and you have more CH bonds, right? So that's one way you can use a hydride. You can use it as a nucleophilic, you can use it as a nucleophile to knock off a halogen in an alkyl halide. Does that make sense? No. Okay. Right? There's something else you can also use this on. This can react with everybody's favorite type of molecule. The epoxide. Ooh, epoxides. Actually, I had a good example written down. I forgot what it was. Okay. Yeah. And again, this is really nothing new. We've seen this reaction of epoxides before, just not with hydride, right? So again, you got hydride. What do you think it's going to do? What do epoxides like to do in general? Yeah, epoxides like to break apart. So if a decent nucleophile comes in, like this H minus, it can attack one of these carbons. Which carbon's going to get attacked, the left one or the right one? More substituted or less substituted? Less, because the oxygen is neutral. Yeah. So yeah, that is just a ring opening of an epoxide with a nucleophile. The only difference is you're using a new type of nucleophile. Right? Now the water does appear in the mechanism. That negative oxygen can grab a hydrogen and viola. You have your product. Product of this is always some sort of alcohol. product of this above reaction is always going to be an alkane. Right? I hope you're starting to see as we go along, there's some patterns here. Certain reactions or certain reagents always make certain types of products. If you try to memorize every single little reaction and possibility, you're going to go insane. However, you can memorize some of these general patterns. Know that an epoxide reacting with a hydride will always give you an alcohol. That's useful to know. Okay, does that make sense? So again, just kind of my PSA that I give every so often. Be proactive, keep organized, remember these patterns. All right? Cool, cool. Any questions about any of the reductions that we've gone over? Right? They've all involved hydrogen in some way. Does that make sense? All right. All right, got just a couple of minutes here. I want to sort of just introduce you to the next section. All right. We've been talking a lot about a lot of different ways to reduce certain organic compounds. Of course, there's going to be some specific oxidations. And to do oxidations, we need oxidizing agents. So let's just take a quick look at some of the oxidizing agents. Ooh, excuse me. Basically, they're going to fall into two categories. And the first category is going to be species that have OO single bonds. Right? Second category is going to be compounds that have metal to oxygen bonds. Sometimes they're single, sometimes they're double. All right? Now, even across categories, all these oxidation agents that fall over here, they have commonality, a certain commonality. These bonds are very easy to break. So they're fairly unstable species. And we take advantage of this fact to create certain reactive species that will then oxidize other things, right? Now, there's a bunch of specific examples within each one of these. We're about out of time, so I think this is a good stopping point. We will pick up there on Monday and go over them, all right? We're gonna make Monday our regular quiz day. We'll have a quiz on Monday over the alkynes chapter. Right. That is all I got today. Hope you guys have a great weekend.